Assalamualaikum warahmatullahi wabarakatuh. I am Sukuhai, and today we will give you a summary of Chapter 4, which is 4.1 Functions, 4.2 Linear Models, 4.3 Inverse Functions, 4.4 Arithmetic Sequences and Series, 4.5 Linear Regression. Without further ado, let's move on.
So for the first subtopic is 4.1 function. Function is a relation, a set of ordered pairs x and y that specifies corresponding values of the independent, which is x, and dependent, which is y, variables. A graph is a one way to represent a relation between two variables. Below you can see the difference between a function and a not function. Easily we can say that for each x value there is only one corresponding value of y, which is for one input there is only one output. So you can see at point number C, and if the x is 2 and the y is 4, so it only have one. But if it's not a function, if you say that x is at 0, the relation is not a function, s is at 0 and the y has two values, which is 1 and -1. So this is not a function. So let's see through the example. So I think we can see here, for each relation determine with a reason whether y is a function of x. So I'm just going to skip it to point A. It says in an annual survey of panda population, x equals to time in years since 1977, y is the number of pandas. So is it a function or not? It is yes, because each year we will only have one measurement of panda population. It will be no if we have many number of panda population. Okay, so we skip the next part. The second part is function notation. How do we write function? So easily we can write a function by giving it a y equals to fs or fx equals to y. Or you can also say that y is the image of x under the function y, under the function f. So in function notation we have two factors, we have two values. The first one is domain and second one is range. Domain is a set of all possible input values of x, while range is a set of y values, the outputs corresponding to all the inputs in the domain. So let's say we have the function fx equals to 7 minus 1 over 3x, and the domain is -2 lesser and equal to s lesser than 4. So we know that our domain, which is the input, are -2, -1, 0, 1, 2, 3, 4. And the range, we have to find the range by substituting the domain in the function. So let's say we substitute 4, x equals to 4 into the function, then we will get 7.67. So that is our upper bound. So if we substitute the lower domain, which is -2, into the function, we will get 5.67. So the values between the lower bound range and upper bound range is our values for the range. So we move to the next part, which is 4.2, the linear model. So a linear model is a linear function fx equals to ms plus c, where m and c are constants. It represents a context with a constant rate of change because it is linear. So the constants in an equation are called parameters. A linear function has a parameters gradient m and y-intercept c. So we can recall that we have three different common ways that can represent a linear equation. So you can see at the table below, the gradient intercept form, the point gradient form, the standard or general form. Okay, so let's skip to the example. I think this is quite simple because we have learned it since primary school. So let's see the example. It says a water tank drains at a constant rate. It contains 930 liters of water. 3.5 minutes after it starts to drain. It takes 50 minutes for the tank to empty, and let W be the amount of water in tank T minutes after it starts to drain. So we have to find the gradient intercept model for W function. So like I told just now, function notation starts with fs or any function it can be, but the question here asks it to be wt, which means W is the amount of water and T is the amount, that is the minutes that you have to input. It is the domain. So I think you can read this by yourself. So I think we move on to the next chapter, which is 4.3.
Okay, we move on to the next subtopic on this 4.3 chapter, which is inverse function. So basically, what is inverse function? Inverse function can be defined as a function which can reverse into another function, or in simple word, if f and g are inverse function, then f function equal to y, if and only if gy equal to x. So we have seen how a regular function turn a into b. The inverse of a function turn those b value back into their respective value, reversing the operation. Uh, you can simply see on the example below on how inverse function are illustrated. Next, how do we find f inverse? Okay, let's say we take f function equal to x plus 10 as our example. So the first step is we need to set f function equal to y, then solve for x, and last one we need to keep the solution but replace y by x. Therefore, we got the inverse function of f, which is x minus 10. So this is some example of inverse function question that I took from the textbook. You can go through on the question one by one because it's quite simple and direct question. Next is equation and graph of inverse function. So because the inverse function reverse the input and output of function, you can find its equation by switching the variable s and in the equation for function. This is some example of this topic, and I think you can read only by yourself because it is easy to understand. And the last one that I want to highlight on this 4.3 topic is composition and the formal definition. So you think of an inverse function as reversing or undoing a function. To formalize this in a definition, you need a way to show that you are performing more than one function in a row. So since we are facing time constraint, I think you can read by yourself on the example below on how composition function were illustrated. So this is some example of composition question. You can look at the example and make sure that your composition equation is correct. Then you can use GDC to find the value. So I pass to Engku to continue this presentation.
So I will talk about 4.4, which is about arithmetic sequences and series. So we had already learned this during our secondary school, which is chapter 1, form 5 in the KBSM additional mathematics syllabus. So this chapter is just want to refresh our understanding and knowledge. So these are the list of the formulas that we are going to use in the arithmetic sequences and series. So I hope that you all still remember what A, D, N, and S refers to. Okay, so let's move on to a few examples. Examples of finding D using the formula. So D is the common difference which differentiates um, arithmetic sequences and geometric sequence. Geometric sequence use R, which is ratio, but in arithmetic we use D. So finding D is simple. We just need to put the information inside the formula. So as you can see from the example, yeah, it's very simple. And moving on, we also have a real life application, which is what we usually get in our examination paper. So yeah, in this example, we are given a pile driver, which is a machine used in construction to drive support poles into the ground by repeatedly striking them. And as it strikes the ground, yeah, it goes 0.12 meter deeper into the ground. So yeah, as you can see that it is constant, therefore it is arithmetic sequence. Next, we move on with to arithmetic series, which is the sum of a sequence denoted by the term s in the formula. So this is a sum of the terms. Basically, this is sum of the terms in the arithmetic sequence. So
can just look at the example. It is very easy, so I hope that uh, this will refresh your knowledge in secondary school. Okay.
So now finally let's go to 4.5, which is about linear regression. So in previous section you have developed a method to model approximately arithmetic sequences. Therefore in this section we will investigate how you can model approximately linear situations with linear models. In this investigation you will improve on the method developed in chapter 2 for creating a line of best fit. So first let's take a look at basic of linear regression. So here we can see um, there are a few formula for the linear regression. So first is we call it as SRES, or least squares regression line. This formula actually you just have to know, but to calculate you can use GDC. Next we look here, it's the gradient formula. The same thing, you have to know the formula, but you can use the calculator to calculate your gradient. So we move on to the example. This one you can try by yourself. So take a look at the example 20 in the textbook page 193. Then we look at the validity of predictions. So predictions from linear regression are more accurate when the correlation coefficient is stronger. So at least a moderate correlation and a linear relationship should be established before making predictions from a linear regression. So prediction means the interpolation and extrapolation of the graph. So to get more accurate, it is more likely for us to do interpolation, but for extrapolation it's going to be a bit inaccurate, but you can still use it. So let's take a look at 4.5 topic review. So we have already covered the sum of square residuals, or SSRES, and we have already covered about the least square regression line, and or we call it as linear regression equation. And then we have already talked about the interpolation and extrapolation when doing predictions. I think that's all for our chapter 4. So we have already covered 4.1 until 4.5. That's all from us. Thank you.